Good evening and Happy New Year to everyone. I, Zishanur Rahman, welcome at the inaugural session of National Workshop on Statistical Analysis of Biological Data. The modern economists believe the world's most valuable resource is no longer oil, but data. The amount of data we produce every day is truly overwhelming. Recent analysis suggests that more than 2.5 quintillion bytes of data are generated every day. With so much information in the form of data at our fingertips, consider all the ways of interpretations to run a business, to predict future outcomes, and even to rule the world. No research is completed without integration of statistical analysis. All credits go to our fabulous statisticians who provided the basis to collect, understand, analyze, illustrate, and interpret the data to draw a conclusion. At the beginning of our program, we wish to pay a small tribute to the legions of statisticians whose contribution have changed the world. Thank you. The presentation is as follows.
Yes, it is.
Thank you. Thank you, Dr. Zishan and Dr. Savinder.
Welcome.
A very good afternoon to one and all present here. I, Tabassum Jahan, on behalf of the organizing committee, welcome Principal Ma'am, our chief guest, Professor K.S. Rao, keynote speaker, Dr. Raji Sundaram, the guest of honor for today, Professor T.R. Rao, our participants, faculty across different colleges and universities, and dear students. A very warm welcome to all of you to this 5 weeks national workshop on statistical analysis of biological data. Biostatistics is the integration of statistical concepts and tools to the wide range of topics in biology. It is not a new branch, rather it has been used since ancient times to interpret the biological data. Even the nature has not distinguished biology from maths and statistics. It is evident from almost each and every living being. Like the beautiful way a tree branching pattern, root system, or even algae branching system, it obeys the sequence of numbers called Fibonacci series, where each number is the sum of previous two numbers. The shell spirals and the cochlea of our ear and pattern of spider's web obeying the golden mean or phi. The list is endless, encompassing human body shape, animal shapes, reproductive dynamics of insects, animal flight pattern, and yes, even the basis of the life, the DNA. The 34 angstrom and the 21 angstrom also follow the Fibonacci series. So even the most minuscule of the life is not immune to statistics. So we can aptly say that a lot of statistics everywhere in the life. So it is worthwhile and absolutely necessary for a biologist to be aware of the statistical tools that one can use for the meaningful and a more significant analysis of their data. With the concept and the realization of this concept, this workshop is an endeavor of ours to let us biologists become aware of the classic and the latest in the field of biostatistics. With these words, I would request our principal, Professor Sangeeta Pandita, to address the gathering. Over to you, ma'am.
Can you hear me?
Yes, ma'am. Yes, ma'am. We can hear
Yes,
you.
ma'am. Yes, ma'am.
So
Yes, ma'am.
such a relief to
Ma'am,
such a
if you
relief. Yeah, I will do that. Yeah, you can
Yes,
see me
ma'am.
now?
Yes, ma'am.
Okay.
Yes, ma'am. Definitely.
Yeah,
Thank you.
good evening, and thank you very much, Dr. Tabassum. In fact, the previous speakers also have given almost everything about the seminar day course. But I would I'm happy to be here and welcoming all the distinguished speakers that you have, a galaxy of speakers. I'm also wanting to really listen to them eagerly. And you have really chosen a good time because evening time is when the office is a little easier, so I can spend some time listening to our distinguished speakers also. This is a wonderful area to hold a course and a 5-week course, long course on this particular area. Especially so because we are grappling with the public health problem for the last 2 years. That is where the statistical part of it is also helping us in many, many different ways. You see all kinds of statistics around the pandemic that we are facing. Not only that, generally in public health, it has been of tremendous importance. But before that, I think each one of us has some little encounter with little kind of statistical things that we do in our own lives. In the manner that I would say that these statistical data will help you discover something. I personally would relate a simple kind of experience that I had. You see, once one of my children got infected with the amoebiasis, and he was given a medicine called metronidazole, which all of us know about. Well, after the course, 5 days course, after the course, third day he developed some rashes, and I take him to the doctor again. Because I have a habit of writing which dose was given when, all the details I have written. And also I have written that third day after that, he gets a rash, which the doctor identifies as idiopathic urticaria. Well, a few months later, he gets a similar infection and is given the same medicine, metronidazole. And this whole pattern repeats. That is, after the third day of completion, again, the same idiopathic urticaria. Then I report to the doctor with my statistical copy. I say this is not ordinary urticaria, perhaps it is related to the drug that is given. And yes, he was rather relieved and he said, I'm glad you made such notes because, yeah, there is a discovery, the boy is allergic to metronidazole. And from then onwards, this is a small story, which I found was very powerful. It told me a lot about, I discovered that my son was allergic to metronidazole and hence tinidazole was rather prescribed. So this is what I mean. We have our own, we develop that attitude of having a statistical way of looking at things. Then things become much more, easier to handle, predict, and manage at times. Also discover. That's the basis of science. And the amount of data that is piling up these days is phenomenal. These statistical methods that you learn over these 5 weeks, I'm sure will go a long way in giving you a solid footing in the source and in the sciences that you are opting to study further. So I think, congratulate you for choosing such a wonderful topic for the course to be done. 5 weeks is a long time. You can lose interest, but I'm sure your organizers have taken care of that, and they will be meeting you frequently to take care that you are back again into on the task. So thank you very much for inviting me here. I'm really, really glad to be here and really happy to see that you have a wonderful spread of speakers. I'm going to stay on for some more time to listen to your next speaker. Thank you very much and welcome everybody.
Thank you so much, ma'am, for your kind words and the encouragement. Now, I would request Dr. Ratnam Kaul to kindly introduce our chief guest for today, Dr. Professor K.S. Rao, and welcome him for his inaugural lecture. Over to you, Dr. Vatil.
Thank you, Dr. Tabassum. A very good evening and a very warm welcome to our esteemed guests, principal, colleagues, and participants. It is indeed a pleasure to introduce our chief guest, Professor K.S. Rao, to our participants. Professor Rao is a senior professor in Department of Botany, University of Delhi. He is also Dean, Faculty of Technology, University of Delhi. He has been a very active researcher who has research interests with abiotic stress and climate change adaptation, natural resource management, sustainable development in Himalaya, and biodiversity assessment. He is a highly decorated scientist with Vishisht Vaigyanik Puraskar by Ministry of Environment, Forests and Climate Change for his exemplary work on Nanda Devi Biosphere Reserve. Another feather to his cap is the UGC National Swami Pranavananda Saraswati Award for Ecology and Environmental Sciences for his contribution on sustainable development of Himalaya. As an enthusiastic teacher and an accomplished researcher, he has supervised 25 masters, 3 MPhil, and 20 PhD students for their degrees in various universities and has published about 25 books and more than 350 research papers in both national and international scientific journals and books. He is a member of various academic and scientific societies such as National Academy of Sciences, Allahabad, an elected fellow of National Institute of Ecology, International Society of Plant Morphologists, the Indian Botanical Society, and the Linnean Society of London. With this brief introduction, I now invite Professor Rao for his lecture. Thank you, Professor Rao, for sparing your valuable time. And over to you, sir.
Good evening. I hope I am audible to you all.
Yes. Sir.
Thank you for introducing me. I'm happy to be present here in the National Workshop on the Statistical Analysis of Biological Data. As a chief guest, it's my responsibility to promote this course first. So I take this opportunity to present to you a small story so as it is promoted. So my presentation is predominantly a story rather than any scientific work. I take this opportunity to thank the principal, Professor Sangeeta Pandita, for giving me this opportunity along with the organizing committee from the college, and also Professor T.R. Rao, the senior teacher, who is exponent in actual statistical teaching. In front of me speaking statistics is really worry for me, actually speaking. In any case, I will take a little courage and make this presentation. Let me share the presentation. I hope the slides are visible.
Yes, sir.
Yes, sir.
Okay. So look at this, a graph where two factors has been assessed and a data that has been there has been fit into the best fit curve. And there is one data point which is not following the trend. We simply call it as the outliers of the data. But the data point says your theory itself is wrong. So it is how we look at is actually making all this change. So whether this outlier is important or not is something is a great part of the discussion in the statistics. A lot of people has been looking at it. There is a statement that says lies, damned lies and statistics. So who has said this statement? If you search for this statement in the internet, there is about 5,100 hits. And really interesting, who said it? In his autobiography written by Mark Twain in 1924, it is attributed Benjamin Disraeli has said this. So we hope that Mark Twain was correctly stated, attributed this statement to Benjamin Disraeli. Did Disraeli said it actually? When we search further, we will find it is not said by him. Who did it? It is Leonard Henry Courtney, a British economist and politician. And the quote can be found in a statistical journal, the Journal of the Royal Statistical Society, published in 1896. So let me take the help of some characters to go for a dialogue. So you already identified this is the Midgate King of the Wizard of ID, and he will be discussing the statistical requirements in biology with his wizard. So you might be encountering these statements. If you think liars lie, try statistics. Paint is to art as numbers are to the statistician, and numbers are to the statisticians what paint is to. People also say, when in doubt, use statistics. Statistics are numbers looking for an argument. When all else fails, use statistical reason. If you want to really lie, use statistics. So all these things actually says that statistics is something which is trying to prove something which may not be true. It's not so always. Geo Ashley has stated that, like other occult techniques of divination, the statistical method was, as a private jargon, deliberately contrived to obscure its methods from non-practitioners. We already know that whenever we talk to a statistician, he talks so much of the technical words that most of the practitioner biologists and the others really get worried what it actually means. And those who doesn't have much knowledge about the statistics or mathematical applications really think that they don't know anything about it. So it's basically the students feel that it is just for the confusion purpose only these statistics are introduced as a course to the curriculum. It also frustrates and mystifies in conjunction for most of the students, especially in biology. And you can also say that man without statistics is like fish without a bicycle. So fish doesn't require a bicycle. It means that man doesn't require statistics. This is what. So the Midgate king says, I am going to abolish statistics from my kingdom. The wizards can't do that. The king says, of course I can. Lord Rutherford says so. What Ernest Rutherford actually said. He had made a statement, if your experiment needs statistics, you ought to have done a better experiment. This means that Rutherford believes that if experiment is done properly, there is no requirement of statistics. And the wizard says, it is an unsourced quote. So, is it really attributed to Rutherford by the? So, it is actually attributed to Rutherford by the NTZ. A Latin square design uses statistics, and thus experiments do require statistics. Now, according to that code, if you use a Latin square design, you should have done experiment then. The king says, once wrong doesn't mean always wrong. King once again emphasizes, I say again, statistics are gibberish. Get rid of so as the people of my country have a life which is easygoing. The wizard tries to convince, saying, Rutherford also did experiments. Here is a quote. So, or a Fisher's experiment, every experiment may be said to exist only in order to give the facts a chance of disproving the null hypothesis. So, let us check. When you check both the statements, you find.
Excuse me, sir.
Yeah.
Sir, sorry to interrupt in between. Sir, are you changing?
I'm sorry for the technical glitch. Okay, when we search for these two statements on the Google, you have that Fisher's statement has more number of the hits. So the wizard says Fisher won the argument with the 5 million hits on the null hypothesis. The king says that doesn't prove Fisher was right. I have it on good authority he was. So what is it? It is extraordinarily difficult to find a statistician who argues explicitly in favor of the retention of significance tests, which is a statement by the 1986. So there are others who also have said that. M.R. Nestler collected over 125 quotes against use of hypothesis testing, and D.F. Parkhurst collected 80 quotes against continued use of significance tests in 1990. John Nelder, who is the successor of Fisher as the director of the statistics department at the Rotham State Station, has actually made a statement. Everyone will have his own pet assortment of driftwood. Mine include most of the theory of significance testing, including multiple comparison tests and non-parametric statistics. So hypothesis testing is malar. Get rid of it. This is what the king of ID has to say. The wizard tries further. Okay, let's not get carried away. Let's get another opinion. So Wilkinson et al. In 1992 has said that you are always better off thinking about why a model could generate your data and then testing that model. So Wilkinson has proposed that biological data constructed into a model using the relationships and it could be tested. So the king asks, what about all this stuff of models? The wizard says, I'm glad you are. Look at these two parts. So when you ask for what test do I use when you have a data set, you have to identify a test by name, check its assumptions, use of automated routines provided in a package. Basically, we will be using statistical packages. At the end, we'll try to review them. Sort through the output for a probability value and report whether the probability was less than 5%. But when you look for the problem solving approach, then you will be looking at what is the response variable, what are the explanatory variables, and then write a model that explains the relationship between these two, check for the residuals, and check whether this model is appropriate, by whether it is best fit or not, what is the error structure, whether the error structure is the correct or not, and then take corrective action if it is not correct. When it is correct, report the model, parameter values, and standard errors. That's all. So the wizard says, learn to write the model instead of memorizing the tests. This is a better way of learning the statistics. So the king says, what? Me write a model. The wizard says, no problem. Can you write an equation for a straight line? A straight line is relationship between the two variables. So the body weight and the number of eggs as a relationship indicates here a straight line with dispersal of the data sets, where you could say data is model plus residuals, which we can express as the y is equal to mx plus b plus residuals. So what are they? Y and x are the variables. The m is the slope of the line and b is the y-intercept. So this is so simple. This is what the wizard says. So the most critical as the biologist, okay. So as a biologist, the most critical part of the statistical analysis is going to be the data and how we look at them as the factors. So the factors are the variables that experiments control during an experiment, experimenters control during an experiment in order to determine their effect on the response variable. So a factor can take on only a small number of values, which are known as factor levels, and that's one reason why normally we use 1 to 1, 1 to 2. As you increase the number of factor levels, you have more complex models that you have to deal with. And for a statistician, the residuals are going to be the most critical one. And a residual is a measure of how well a line fits an individual data point, and thus he will be looking at why this variation is present. Look at this. 3 of the master students collected some data. So I asked 3 of them with the pooled data to draw a regression line. All the 3 individuals has drawn 3 different lines. Why this is so? As a student during my graduation and post-graduation, for drawing a regression without going through the statistical methodology is to look at a line that is passing through the data points where the data points are equally distributed on both the sides of the line. This is what the teacher used to say and we used to follow. So the same thing has happened. But what will happen when you use a proper statistical method? You will be looking at what is the residual or the variation that each of these data point had with the line. Thus, the sum of the squares method that is used for the regression line and how you can look at the best fit method. So statistical tests of assumptions are going to be most critical in terms of what is the hypothesis and how you actually look at your experimental setup. Statistical tests of assumptions are like going out in a rowboat to see if it is too windy to set sail in the lake. So you have to be very careful in terms of what statistical tests you want to. Statistical tests have little capacity to detect problems when it matters because the number of observations are going to be pretty small, means the number of replicates or means that you have apply for the statistical tests are small. When the statistical number of observations you have is pretty large, then the statistical tests can detect small violations when even large violations do not matter. So there are going to be issues and one has to be very careful of understanding what. So thus statistical tests of assumptions reliability lead to the wrong conclusions. But as a biologist, what is that we are actually looking at? The typical assumptions that as a biologist we are normally looking at whether our data has the normality, that is data how normal distribution, homogeneity of the variables, that the data from multiple groups have the same variance, linearity, that data have a linear relationships, independence, that data are independent. Thus, so when we try to build up the relationships to find out what is the best type of the test, then data model and the residuals in terms of the general linear model, when you have 2 means with the normal distribution residuals, then you simply go for t-test. When you have several means with the normal residuals, go for the one-way ANOVA. When you have 2 factors with the normal residual, you will go for the two-way ANOVA. And we have a linear relationship that is a line with the normal residual, that is the regression. When you have line with the factors and the normal residuals, we will go to the ANOVA. So this is how using the relationship and the residuals, you could go for the finding out what is the best type of the test. This is what the wizard has to say. So write the model, discard the search for the tests. So as I said that the assumptions are going to be the most critical one. The statistical tests of the assumptions that we have said, the normality, homogeneity of variance, and linearity and independence. And checking assumptions before analysis is important because that is how you are going to actually check whether your hypothesis is. And then you also have the non-parametric tests. Then you have issues of the post hoc tests because you haven't planned your experiments using a statistical hypothesis before it's actually started. So, as Shin has said, checking statistical assumptions before analysis is like taking rabies shots before. So the assumptions for computing probability value from the FT or chi-square distributions are the residuals sum to 0, residuals are homogeneous, residuals are independent, residuals are normal distributed, which the biologists also are interested in terms of the data points actually. And thus, you will be basically looking at as a biologist for the model that is the relationship part, whereas the statisticians are going to be more interested in terms of the residuals part. So as a biologist, we are more interested in the magnitude of the difference between the groups than we are ranking of the. So as the Penn has stated, the non-parametric tests are an assumption-free procedure for investigating a hypothesis of no practical interest. So the post hoc tests turns lying over to the computer. So the computer will be giving you some probability values and almost always less effective than the planned. Thus, before starting an a priori tests, that is the planned ones, an important mode of biological reasoning, almost always more effective than post hoc test on the comparison. But in practice, we always has been doing the post hoc test because once we have collected data, only then we think about what type of the statistical data treatments has to be. M.J. Crowley, one of the person who has mastered in statistical teaching, has commented that the elementary statistics courses for biologists tend to lead to the use of stereotypes set of tests because we have been said that use T, student T test, chi-square test and all those things without the critical attention to the underlying models or the relationships that are involved, without due regard to the precise distribution of the sampling errors, with little concern for the scale of measurement and the careless of dimensional homogeneity, without considering the idea transformation that is required for the data sets, without any attempt at model simplification, with too much emphasis on hypothesis testing and too little emphasis on parameter estimation. Gary Ramsay's advice on teaching statistics is show students how statistical methodology can have relevance in their life. Above everything else, maintain a sense of humor and don't take yourself so seriously. So you are going to have 5 weeks of intensive training. Also add a little fun in between so as you enjoy the course. So the wizard says, this are the equations. The king says, I don't have time. It is Greek to me. Look at a comparison of the available statistical programs that we normally encounter. As a biologist, I had been using all of them. The spreadsheet most of us use, Microsoft-based one. So the things that you could actually do using most of them are given here. So some programs could use advantages So SPSS, which the Delhi University students predominantly use, actually it is a social scientist based approach, but still a lot of biologists are also use. We used to use Systat or S plus MTAP as a biologist. SAS used to be very big program earlier, but now they also have simplified it into. So the king of ID says, then I decree that all must take this course. So as the wizard has said that they are easy in one of these packages, they can be taught at any level in the university. It is better practice than looking up some test. It is quicker than looking up some tests. As the king has decreed that it must be take the course by all his people in the country. So I also, as chief guest, suggest that all the students take this course. Okay, before we close, the wizard says, let's not get carried away. Let us. So the Bureau of Statistics out for lunch is in big letters, but when you carefully look at it carefully, 67% chance of being back in 1 hour. So statistical small data is there. There is always small lines which you have to be reading when you are dealing with these statistics. Thank you very much for your attention. I will be sharing a small booklet that is a biologist guide to the statistical thinking and analysis for your consumption. The organizers will be sharing it with you. Thank you very much.
Thank you, Professor Rao, for an extremely fact-based story. It was indeed very beautifully illustrated, and you immensely simplified the significance of statistical analysis of biological data. I really enjoyed the illustrations. Thank you once again.
Thank you.
I now take this opportunity to welcome and introduce our keynote speaker for the evening, Dr. R. Sundaram. Dr. Sundaram is a senior investigator, Biostatistics and Bioinformatics branch, the National Institute of Health and National Institute of Health, USA. She is an alumnus of University of Kolkata for her undergraduation, master's from Indian Statistical Institute, Kolkata, and PhD from Michigan State University, USA. Her major research areas are reproductive health and environmental epidemiology. She is one of the most meritorious researchers whose thesis was nominated for the best doctoral thesis from Department of Statistics and Probability, Michigan State University. She is a proud recipient of Griffith Mentoring Award, Outstanding Statistical Applications Award, and many more. The list is long. She has contributed towards the teaching assignments, thesis supervision, editorial service, journal peer review, to name a few. She has also very actively participated in the organization of symposia and workshops, and is also a member of several academic committees. With this brief introduction of Dr. Sundaram, I welcome Dr. Sundaram to the workshop. Good evening, Dr. Sundaram, and my apologies for interrupting this lecture of yours. I'm sorry, Professor Rao, if you are still connected. If there are any questions from the audience, a flap on my part, I missed out the question answers. Apologies for that. So if there are any questions, please raise your hands.
My lecture is predominantly promotional lectures. I don't think there is any real confusion in terms of.
No, absolutely not.
You exactly filled in. I'm giving more case studies. So I was thinking there is a need for talk like yours before mine. So you did a fantastic job. From my point of view, definitely, and I think the students would be appreciating it too.
Thank you very much.
So do we have any questions? Or Professor T.R. Rao, will you like to say something here?
No, I'm just enjoying. Thank you.
Thank you, sir. So, sir, thank you so much, Professor Rao, once again. And since there are no questions, we'll go to Dr. Sundaram. So over to you, Dr. Sundaram.
Thank you so much for your introduction and for the previous speakers for fantastic introduction to statistics. So this makes my life easier. So let me first get the logistics part of setting up things clear so that just let me know if it's yeah, all right. Let me, can you make it full screen? And then I'll take back the control. Let's see. Dr. Rahman, was that Dr. Rahman? Okay, let's get started to save time. So you'll have to bear with me. I'll have to look at the screen over my laptop in icon size. So good evening and good morning here in US. And I really want to thank the organizers for inviting me. So what I'll be speaking today is more like case studies of think about how statisticians can make an impact on biological. I work more on the clinical end, but I can tell you, being in National Institutes of Health, for people who are not aware, it's one of the premier research institutes in the world, which does research in biology and clinical ends. And we are very active in the pandemic response for people who track information worldwide. I'll be speaking on basically issues on rising cesarean rates and how can a statistician help. And can you move to the next slide? Okay.
Yes.
A little bit about myself so that you know, personally, I wish I was there in person in Delhi rather than doing it remotely. Even though, as you know, my name suggests I'm Tamilian by my roots, but I grew up in Ludhiana. So Delhi used to be always the stop point for me whenever I went out of Ludhiana. So as a city, I love it. So I really envy you guys. And I've been stuck in pandemic for, in US for a long time, not going back to India. I did so on a personal end, this is really a joy. And professionally also, I feel that if I can, encourage students who are interested in learning statistics and biostatistics, it's amazing. I benefited a lot from the Indian system, and I feel that it's time to pay back also. As you were told about my background, I just want to point out I gravitated from mathematics to applied statistics, back to mathematical statistics, and now I'm very much in an applied statistics world. I actually work at a cusp of statistics and clinical. Can you move on to the next slide? I think, let me take control one more time to see, because it will help me. Okay, the second I take control, it becomes much smaller, so I will let you take back, sorry. Yeah, so what I'll be doing is giving you a little bit of background and then talk about two case studies. And the first one is going to be a clear example of classical statistics. And the second one is a cutting edge methods application of artificial intelligence and machine learning. And I don't think I'll have time to go beyond that, but it's a totally non-technical talk, but just to explain to you how statistics can play a significant role. And can you move to the next slide? Thank you. Yeah. So as I said, I'm interested in looking at the cesarean delivery rates. My example, motivating example, comes from obstetrics. And so people are mentioning that the slide is remaining at the same. But in my case, I'm able to see the newer slide. So when you look at the world map and you look at the percentage of C-section rates worldwide, the red and the dark red clearly indicate increasing rates of cesarean delivery. Now, can you move to the next slide? Okay, so so as a statistician and as a biologist, what you need to learn to start looking at are a lot of graphs, and what is an important part of statistics. Professor Ram spent a lot of time discussing about models and statistical significance and the importance of it. But another aspect that I feel is very critical is what's called descriptive statistics. So that means, how do you summarize your data? How do you best describe? So graphics play a very critical role. So when you think about cesarean section, in the previous graph, I showed you the world map, and it showed that there are high percentages of cesarean delivery happening. So the next question you should be thinking is, oh, it's high, but may have been high all over. Why do I care? So what you need to look at next is the time trend, and that's exactly what you tend to do. When you look at this graph, this is showing information from 1980s to 2015, and you can clearly see this. All the lines are rates for different regions of the world. And what you see is uniformly an increasing trend. So the problem is not just local, it's the increasing trend is happening globally. So now the next question, next slide, please. Okay, before I move to now, the question in your mind should be, okay, cesarean rates are increasing, why do I care? How many of you are going to think like that? Because a lot of us, are born through C-sections, but do we care about it? The answer, so the answer to that is to keep in mind that cesarean section, when the mother goes through cesarean section, she is undergoing a major surgery. So the question that comes up in mind is, why do we need to get the woman to go through a major surgery unnecessarily? So every time you have a major surgery, doesn't matter where it is done, even in the best of the situations, there are always chances of having complication. I'm not spending time in showing the well-established knowledge about cesarean sections being associated with lot of other complications because it's purely a major surgery. So now the question is, so globally there is a lot of interest in trying to understand from World Health Organization and other. I work a lot with the American College of Obstetrics and Gynecology, being in United States, is how do we take care of, are there unnecessary C-sections? Can we avoid them? But before I move on to little more details, I want to introduce quickly how does a labor happen. For women who have gone through this or dads who have had children would understand, but I think starting undergraduates, you may not be so much aware of it. So there are 3 stages to this progress. In the first one, there is what is called a dilation process, where the cervix dilates from 0 to 10 centimeter. And in the second stage, when the woman fully dilates, she starts pushing out the fetus. And in the third stage, once the baby is delivered, there is a third stage after delivery too, that is called placental expulsion. The placenta that had surrounded the fetus needs to be expelled too. So I'll be focusing on the first and the second stage of labor just as an illustration. And this is, I'm going to go at a pace that you are comfortable with. I don't want to go too fast. If I'm going too slow, please let me know in the chat, okay? So the next slide, please. Yeah, so as I mentioned, why do we care? So cesarean sections are associated with, because it's a major surgery, increases adverse events in women and the fetus. But there are now, the question is, why do doctors, if they know it's a major surgery, why do doctors encourage that? Because if a woman is in labor for too long, there are complications too. So those complications can, I have just listed out, I don't want you to really understand all of them, but keep in mind that it is maternal morbidity. That means the mother can have some complications, or neonatal when the fetus or the newborn has complications. Thank you. Next slide. Next slide, please. Okay, so as I mentioned, there is tremendous interest focus with World Health Organization and American College of Obstetrics and Gynecology in trying to reduce unnecessary cesarean section, because what is considered an optimal rate is 10 to 15%. But currently in United States, it's around 32 to 33%. And globally, I want to say it's around 19 to 20%. For people in India, it is also increasing. And India also has an increased percentage of what's called elective C-section. And this is a trend that you see in India and China, that there are a lot more elective C-sections than necessary. So now, so there is an international emphasis, World Health Organization brings out white pages. That means brings out people, medical professionals, encouraging them to try to look at C-section rates and other aspects and say that try to reduce unnecessary cesarean deliveries. So now you understand that there are two things playing over here. C-section is needed because if the labor is too prolonged, the mother and the fetus may be impacted. Now, on the other end, you can have C-section is also a major surgery which can lead to complications. Now, what we want to do is we want to hit that sweet point where the unnecessary percentage is reduced, and then hopefully without having too much increase in risks for complications. So that's the place where statisticians can play a role. So as you think, it becomes more a quantitative question. If a woman is getting to be at a risk for medical intervention, but you want to also think, is she also at an increased risk for complication? So if they don't cross, think about it as two functions. If the crossing point is much later, then you can let her have a prolonged labor, okay? So it becomes more a statistical question of interest than what the clinician. So what we try to do as biostatisticians, that's why it's called a biostatistical, when you live in biostatistical world, you are basically trying to do what's a team science. Professor Rao clearly pointed out examples of using in botany, and you'll be hearing over time of various applications. I kind of am illustrating through clinical end because that's my area of expertise. But think about it as a statistician, you come in, you learn the background. The last time I had a biology course was in high school. So, I went towards physics, chemistry, math background in undergraduate. So what I find very interesting is, as a biostatistician, I get to learn a lot of new things depending on what area of focus I'm in. Right now, I spend a lot of time in obstetrical world. And so when you are as a statistician, I kind of want to convey the philosophy behind what a biostatistician does. So in this example, we try to find the optimal time for when the C-section can be done and is it necessary or not. Next slide, please. So when you start looking at it quantitatively, what is the quantity that you're going to measure? Think about it. If you are tracking blood pressure, if you want to look at heart health, you track the blood pressure as one of the factors, right? So in labor, what do we track? The duration a woman is in labor. So as you saw, there are 3 stages of labor. So we track the first stage, time duration of first stage, time duration of second stage, and time duration of third stage. So the third stage is a bit neglected one, but that's also an important one because once the fetus comes out, she still needs to expel placenta. Lot of time what happens is, which is very frustrating for a woman, that she has delivered the baby normally, but the placenta is not coming and they have to do a medical intervention on her, which can be very frustrating. So C-section can happen in all these 3 stages, the first stage, the second stage, and the third stage. And main reason, as I've written over here again, what those stages are. So what we try to do very carefully, statisticians, is based on the information, the data that we have on deliveries, we try to identify what is a normal progression, normal amount of time needed in each stage. Next slide, please. Yeah. So I'm going to start with first stage. Now the question is, what are the challenges in first stage? These are type of things that you will encounter in a lot of different situations. So I'm just illustrating over here. And in medical, so if we are tracking the time for her dilation from 0 centimeter to 10 centimeter. That's the maximum a woman can dilate. And what the doctors will do is, they're not going to continuously track her at that time, because it can take hours together for a woman to go from 0 to 10 centimeter. So they will come in the middle, they'll send the nurse to come and check and see how much she has dilated and so on. And they will keep tracking how many centimeters she has dilated every visit. So these are what are called intermittent examination time points, medical examination. And how frequently doctors check on the woman depends on how fast she is dilating. If she's dilating very fast, they're not going to leave her alone. They'll come back within 10 minutes or half an hour, depending on how she progresses. But if she's slow, then it can take hours. So they'll come every 2 hours to check on her. So the frequency is a function of how fast or slow she is dilating. And why does that matter? The more times they check on a woman, the more data you have. So keep in mind, as a statistician and as a biologist, when you start doing data analysis, data is power. So if you have more data, that's more power. But what happens if you have less data on a woman? She's not doing it, so she's progressing slowly. They don't check on her frequently. So are you going to penalize her because you don't have enough data on her? So that is where the nuanced statistical methods come, which correct for how many observations do you have on the woman. If a woman has 10 observations, do you give her extra importance compared to a woman who has only 2 observations from the doctor? No. So there are statistical techniques which will balance them out, and you have to pay attention. And another thing that happens, which is statistically challenging, is very rarely woman is going to admit herself when she hasn't dilated at all. So most of the hospitals or nursing homes will not take a woman unless or until it's a planned C-section, will not take her in if she's not 4 or 5 centimeters dilated. So what do you do about the unmeasured time? So you don't know when her 0 point of 0 centimeter to 4 centimeter happened. You only know her from the time the doctor started observing her. So accounting for all these complications, so that's where you have to wear your statistical hat on trying to see how can I correct for all this information and come up with a trajectory for how she's progressing. Next slide, please. Okay, I'm not going to talk too much about the methods. We did develop some state-of-the-art method which corrected for this unaccounted for time, and as well as the amount of data you have on each person. Keep in mind, the more a doctor observes her, the more information you have. Now you can think, so a question that should come to your mind when you start looking at data is, then why not make the doctors check her frequently? Why not say every half an hour, every patient needs to be checked? The reason is, the second the doctor checks, she has an increased risk for infection, because a foreign hand is entering her to check her progression. So you do not want any checks to be happen unnecessarily. So whenever you get data, you should always think about why something is happening. Never take the data on face value. Could I have had what is called a balanced design, that is same amount of data on each person? It may be desirable for a statistician, but in this clinical setting, in a lot of biological experiments, you will see that having equal amount of, or what's called balanced data, is not possible. So what we did is we tried to correct for all this information by developing new techniques. As a fresh statistician or people who are getting introduced, I don't want you to be focused on how we did it. I want you to focus on what were the challenges and why we needed to pay special attention and what do we benefit. My take home for you guys when you go back out of this talk is to appreciate the fact that you will always look at an experiment and the data with very careful attention. Start with describing, then put your underlying models very carefully, and then see what you get. Okay, so the next slide. Okay, what I'm going to show to you are analysis based on what we did on analyzing two big studies that have set the standards in United States. The first was done in 1950s and the second study was done in 2000s. These are what have defined the clinical practices in United States. Being in National Institutes of Health, we did both these studies because we are at the nation's institute in charge of reproductive child health and obstetrical health. So I'm only going to point out two important factors. I'll be calling the first one the CPP, which is the old study, and CSL as the new study. The amount of deliveries that we have in these studies, the top one is around 50,000 and the bottom one is around 225,000 deliveries. Now the point to keep in mind is we are now you see from 1950s to 2000s, the change in the amount of data. We went 4.5 times the amount of data, right? In 1950s, we had only 50,000 deliveries that we were tracking. Now we are able to track a lot more. Actually, this study, the second one, which I will be calling as new study, has become old. We are trying to go towards million deliveries and try to get a sense of it. So next one. Next slide, please. Yeah, thank you. So now, as I said, I'm going to illustrate our methods on how we can benefit by doing a very careful analysis. So there are processes that we are interested in. One is what's the dilation. A woman dilates from 0 to 10 centimeter. And the examination process. How often does the doctor check on her? And the third, which is the most critical one from the Cesarean rate, is what's called gap time. That means how long does she take to go from 1 centimeter to 2 centimeter, 2 to 3, 3 to 4, the gap time, and how long does it take for her to go. If she starts taking too much time to go from 4 to 5 compared to 3 to 4, then the doctors start worrying, is she slowing down? Is this normal? Is there some complication happening? So that's what we want to try to address. And the two main risk factors which play a critical role in this is a woman's age and her BMI. So those are the two that we will be tracking and trying to study their impact on the dilation processes. Next slide, please. So when you look at the graphical display, one thing is, as I said, describing your data is very important. When you look at this graph, the left one is for the older study, the right one is for the newer study. These are what are called the bar plots. In the x-axis, you have the dilation, and the y-axis is the proportion of women who were this much dilated at admission. Now, when you look at these two plots, keep in mind CPP is the older study and CSL is the newer study, 1950s and 2000s. So as a statistician, the first thing you need to think when you look at this graph is, what story is it telling me? I can clearly see in the newer study that women are getting admitted at earlier time dilation compared to women in the older studies. So does that mean that the women are more sensitive to pain and joining earlier? That is one way of going to the hospital earlier. That's one way of looking at it. And the other way of looking at it is they are better at care seeking. So they realize they have started dilating, they get themselves admitted to the hospital. All right, so always the rule one that you should keep in mind, if not anything else from my talk, is describe, graphically display, understand what it says, okay? The next slide. Next slide, please. Yeah, and then I've shown so far the importance of graphical display. Now I'm going to illustrate the importance of describing the data. This is just, as I said, there are two important factors we look at: age and BMI. Age of the mother and the BMI of the mother. And this is, BMI is not after she, when she's 10 months pregnant. BMI over here is at the time she got pregnant. So when you look at it, what I presented are the 25th, 50th, and 75th. I want you to focus on the age first. When I look at the 50th percentile, for those of you, I think you have all learned what the percentiles are by now, but half of the women, so when you look at the 50th, half of the women are going to be younger than that, and half of the women are going to be older than that. So when you look at this number, you can clearly see in 1950s, half of the women were, the 50th percentile was 19 compared to what you see in 2000s, which is 24. So women are getting older when they are delivering their first child. This is the information when they are delivering their first child. Now, when I look at the BMI, that is where the story gets very strong. And you can clearly see the 50th percentile in 1950s for BMI was 21. And when you think about BMI, what is a normal BMI? A number between 20 to less than 25. So that's a normal BMI, in fact, closer to being underweight. But it's a healthy BMI, 21. But when you look in 2000s, look at her BMI. The 50th percentile is 28.8. And that is, a woman is overweight. So that means her BMI is more than 25, but at most 30. That's the region for being overweight. So she's close to being obese, in fact. And these are young women who are so overweight. So now the question that comes is, they are otherwise healthy. Are these the reasons behind prolonged labor? But these women are otherwise healthy. They can be, it's just because they may be overweight, they're taking longer, they're older, they're taking longer. So why should the doctors be rushing in to do a C-section on them? Because they're taking too much time. This may be the contributing factors. Next slide, please. Okay, so what I'm mentioning over here are the various models. The point to keep in mind is I don't want you to take away anything besides that we have modeled the dilation process, we have modeled the examination process, and the other quantity, which is an important one, which we cannot ignore. A woman could have been laboring at home before she got admitted. You know, if she's surrounded by people who are more experienced in it, they'll say, oh, you are not in any rush to go now. You still have long ways to go. She may be staying at home, or she may have delivered before. She knows how her trajectory is going to be. She doesn't show up. So, but you need to account for that unmeasured time, which nobody knows. So there is a model. So we modeled each of these quantities carefully. And there is I have underlined two things. I just want you to, when you learn what's called time to event analysis, you will learn these models. I don't expect you to know anything besides the name right now. And the second line is what says subject specific random effect. If you remember Professor Rao's slide, he had a beautiful slide where he talked about outcome, which was your Y, and he said model plus random error. So the model comes from biologists and the random error comes from statisticians. Statisticians use random errors in two ways. So the random effect is that random error. One is to capture things which are outside of what the model specifies. For example, two people with same height are not going to have the same weight, right? There are other factors which are unmeasured. So the random effect captures that, or the random error. Another place where we use is when we are doing this multiple models on the same person or the same subject, you want to induce a dependence, because how fast she dilates is also going to dictate how many examinations she has, as well as when she gets herself admitted. If she's moving very fast, people are going to rush her to the hospital, right? So these three are linked, and this random effect will capture the dependence. So statisticians typically use it for two different, there are other places too where they are used, but the first one Professor Rao pointed out, and the second one I'm showing where we use. Next slide, please. Yeah, so we did all that thing, and again, so this is the shape of, so we estimated what statisticians do is fit models and estimate how the data would be distributed for them. Now the dashed line is for the new study that is in 2000s, and the solid line is for the older study. Now this is unmeasured admit time. And as I said, whenever you look at the graph, you need to understand what story it's telling. But before that, you need to understand what it is presenting. On the x-axis is the amount of unmeasured time, and on the y-axis is the percentage of data that we have detected, which would have been with that amount of unmeasured time. Now, what stands out to me is, you see the solid line, what we say is skewed to the left, right? It's tilted on the left. And the dashed line is more on the right. That means there is a higher percentage of data with more unmeasured time in CSL than in CPP, okay? And so you always have to, whenever you do, I'm a big believer in graphs because that conveys to picture is worth 1,000 words. Keep that in mind. And that applies every time you do a statistical analysis. The next slide, please. Okay, I have. Okay, all right, perfect. That would be fantastic. So because I do want to point out the artificial intelligence. So, so what we were talking about is the importance of the graphs, where here this is the estimated unmeasured admit time. The point you have to keep in mind is we did rigorous statistical modeling over here, and we were the first to ever come up with the unmeasured time, a proper estimate, rigorous statistical estimate of how much time is typically unmeasured. And this is what we came up with. So this helps clinicians a lot when they start looking at this amount of information. Oh, this is the percentage of time. This is the time she may have been laboring without us following her. So, and that helps them also dictate how to treat her, how to handle that patient. The next slide, please. Okay, I'm not going to go through, and when you fit statistical models, what you come up with are what are called regression coefficients that estimate the impact of a covariate, in this case, age and BMI, their impact on how fast she's dilating or how slow she's dilating. I have color coded it as blue as slow and red as fast, okay? So, and what you look for, you see there is what's called a point estimate, a number, and then two numbers in parentheses. That's called a 95% confidence interval. So that's where statisticians get into trouble and become the, people make fun of us. We only always say things with 90% or 95% or 99% guarantee, because we can never be 100% sure. We have a random noise added to our models, right? How can we be 100% right? So when you look at these intervals, a typical confidence level attached to an interval is 95%, which is usually reported in most of the journals. And if there is a 0, that means that particular variable is not what is called statistically significant. You again heard a little bit of introduction from Professor Rao about it. So you can clearly see that dilation process, age has an impact, significant impact on dilation process. And you see a negative value. That means the older the woman is, the slower her dilation is, okay? And you will see a similar impact on from obesity also. I'm not going to get into more details than pointing out. So, but this is usually a very important product of a statistical analysis, okay? Next slide, please. Okay, and the other thing is, this is very interesting. Who are the women who get admitted later? Okay, so age and BMI and their impact on unmeasured admit time. And again, when you look at it, you can see clearly, I'm only going to point on the CSL, that is a newer study. Age has a positive significant impact. That means women tend to get admitted earlier, the older they are, because they are more worried about their progress. They want to, they're conscious that they're older, they want to get admitted earlier, okay? So they will have a shorter time to, so sorry, I misspoke over here. So that means they have a longer unmeasured admit time, the women who are older. So they are more confident, they want to hang back and not get very nervous. Younger mothers are typically more nervous, so they will tend to get admitted earlier on. So always look at the numbers very carefully and try to interpret. Next slide, please. Okay, and now this, again, this is a table with lot of numbers, but I only want you to focus on the labels. So what I'm presenting over here is, this is what is the most important thing for clinical use. So this is estimated percentiles of gap times. All of you have used, have given exams and so on where your scores come out in percentile, right? How does that mean? It means that you are, if you get a 95th percentile, that means 95% of people scored below you and only 5% scored above you. So you are among the highest. So what I'm presenting over here are 3 percentiles, 25th, 50th, and 75th. Remember, I said one of our interests is the gap time. How long does it take from 0 to 1 centimeter, 1 to 2 centimeter, 2 to 3, and so on. Because the doctors, if they feel she's not progressing fast enough, she's stalled, they will go and do a medical intervention. So what these tables will tell us is, if she was tracking her whole trajectory at 75th percentile, then a doctor should not get nervous if she continues at that. If she goes to 99th percentile, then he or she should be worried, okay, this woman is slowing down big time. Maybe I need to check on her and try to see why that's happening, okay? So these percentiles become very useful for doctors. They actually love this type of tables in obstetric world. They look at, take a woman's age and BMI. Those are the risk factors that they always like to look at. And they want to see how fast or how slow she's going. And our point is, if a woman was tracking at 25th percentile throughout, then she's okay, she's a fast mover. But if she was tracking also at 90th percentile, but throughout at that pace, you should not be worried. You know this is a slow mover. You don't need to unnecessarily go and intervene. Only thing is that if she ends up taking inordinately high time, then you go and intervene. Just track her and track her vitals and the fetus's vital, and don't go and do a C-section or other interventions unnecessarily. So that is how we can help with numbers. And this type of data-driven clinical decision-making is becoming more and more important in nowadays with a lot of data that's available. Next slide, please. Yeah, so as statisticians, as I said, I love graphs. So these are what are called, again, you will learn what survival distributions are once you take some statistics courses. This is a very important graph that we typically do. And what these graphs are showing are the time a woman takes to go through 0 to 1, 1 to 2, and so on. There are 10 centimeter dilations, right? Doctors are trained to measure the dilation in increment of units. So that's why I have 0 to 1, 1 to 2, and so on, gap time distributions. It's like how long is she waiting in a specific dilation before she goes to the next one, right? And the way to interpret these plots is, again, I've done it for CSL and CPP. Solid line is CPP, dashed line is CSL, and x-axis is the amount of hours, and y-axis is what's called survival probability. That means probability, I'm assuming you're familiar with the term probability. Probability is the chance that a woman is at a specific value, duration, and still in a stage. If you look at W4, that's the waiting time for 4th centimeter dilation before she moves on to 5. So so you see the survival curve start at 1 and then drop down to 0, because everybody enters 4 centimeter and then they exit out of 4 centimeter. So the probability of remaining in 4 centimeter becomes 0. Now, what these curves help us to identify is, at any duration, what percentage of women who have exit are still in 4 centimeter. So if she is taking 4 hours to be in 4 centimeter, that may be too long for, so these curves help us identify what is a reasonable threshold to be in a certain dilation. And again, the point to notice is the dashed line is above the solid line for the 4 centimeter dilation and the 5 centimeter dilation. So what does that mean? CSL, keep in mind, dashed is for the newer study. So if the line is above, that means more percentage of women are still in that dilation. They haven't exited out. So that means CSL, the newer study women, are taking longer than the older study women. And these are all, the point that I did not mention earlier is, which I forgot to mention, is these studies were only of deliveries that resulted in normal with no medical intervention needed. These are healthy women. So naturally, these women are taking longer in the CSL compared to CPP. So it is okay for the doctors to wait out till she moves to the next one and not worry that she is stalled. Okay. So you see that in the 4 and 5 centimeter. Can you move on to the next slide, please? Yes. Aditi, you had a question?
Excuse me, Dr. Sundaram. Actually, our next speaker is also waiting, so I'm afraid we won't be able to take questions.
That's okay. I will wrap it up. So
yeah,
the
thank
same
you so much.
story, So the same story continues for the 9 and 10 centimeter dilation. So the point is, this is where again you can intervene. So this is again to conclude the point that you can do a very careful statistical analysis and help the doctors make a better decision. And can you move on to the next slide? So I have already conveyed the summary findings of what you can do with a very careful analysis. And what we are saying that the newer study always takes more time. I mean, women are taking longer than the older study. So this is normal, not to worry. I'll ask you to keep moving on further and further, and then can you move to the next slide, and then I'll wrap it up. Okay. Yeah, can you go back to the previous? I don't have time, but I'll point out what you can do. Just the previous slide. Yeah. So what I talked about so far was the first stage where the woman dilates. Now in the second stage, once she's fully dilated, she has to push out the fetus. So that is another place where C-sections tend to happen. So what we have done is there are strict guidelines. A woman can be allowed 1 hour to push, 2 hours to push, depending on her underlying characteristics. What we developed are what are called machine learning. Can you please move on to the next slide? What we did is we developed what are called machine learning techniques. For those of you, I would strongly advise you to do a little bit of Google search on deep learning, neural networks, and so on. And that, the advantage of doing the modern techniques is it allows you to handle large data. Keep in mind that CSL had 225,000 deliveries. So you want to kind of use methods which are state of the art, and that allows you to classify whether, so what we want to do over here is build a prediction model. A woman comes to the doctor and you come up with a prediction risk for being at a risk for prolonged labor so that they can monitor her differently. And that's what this type of algorithms do. And it lets us identify what are the important factors that impact. Is it her duration of first stage? Is it her history of diabetes? Things like that, okay? And can you move on to the next one? Yeah, keep moving. Sorry, you'll have to move few slides because I'm going to wrap up now. So yes, please. So please do look into, there are a lot of, nice articles. I'll tell you when to stop. Nice presentations in YouTube on various machine learning tools that you can self-learn. This is absolutely an important one. This has animation, so it will take you through a few clicks. So there are a lot of interesting, tutorials that you can find, and you can identify. I would like you to stop here. Yeah, the previous slide. Previous slide, please. Yeah. Okay. So what you one more slide before. So one more before, and that's my last one, I promise. Yeah. So what this allows you to do is on the left, this is kind of identifying what are the clinical features that are important in predicting a woman will have prolonged second stage of labor. So we have identified the first one is parity. You can see the bar that's so far off. That means if she has had a previous birth, then she's going to deliver much faster. And then the second one we identified is station height. So that means when she's fully dilated, how far down the fetus's head is. And that's the second most important. Makes sense. If the head is very much down, then she's going to push it out faster, right? And so on. So you can basically, these algorithms let you identify what are the important factors. I have listed out over here the top 25. I'll share this with you all. Look at it and please search on deep learning, neural networks, random forests, so on. Those are cutting edge machine learning techniques which are part of artificial intelligence, and that's where I think the data science aspect goes. Now I will ask you to go to my last slide, and that's it. Not the acknowledgement, sorry, the one before. Yeah. So in conclusion, I know all of you are doing, can you go to the previous slide, please? Not the collaborators, the one before. Oh, this is not, next one. Next one. Yeah, this is it. So I know you are all undergraduates in biology, but it's, learning statistics and using it in an informative way is very important. And for though you should know that these disciplines are continuously being ranked at top 5 in United States and worldwide. And we are in an extremely data-rich environment. So being a very intelligent statistician and having skills in biology will make you very, the best in the field, that you're master of both. And I'll stop over here. I apologize for the technological challenges that we had, but at least we have been able to go through it. Thank you for your attention.
Thank you, Dr. Sundaram. And apology for intercepting time and again, because of paucity of time also.
No, of course, of course.
We are grateful to you for the information-packed lecture, which you could not complete. But I'm indeed grateful to Dr. Sundaram for giving this lecture. We were actually quite apprehensive whether she'll be able to deliver her lecture early in the morning, because there was a prediction of snowstorm in Washington and apprehension about the connectivity. I'm also grateful to you, Dr. Sundaram, for giving credit to Indian system and thinking in terms of giving back to society, which gave you what you are today. Thank you once again.
Thank you so much.
I now request Dr. Ruchivi to take the session forward. Thank you.
Please unmute yourself, Dr. Ruchi.
Thank you, Dr. Sundaram. Good evening, everyone. It is my privilege to welcome our guest of honor, Professor T.R. Rao, to our workshop on statistical analysis of biological data. Welcome, sir. Welcome to our workshop. It is our great pleasure to have you in our workshop. Sir is a teacher par excellence with a teaching experience of more than 43 years. Professor T.R. Rao is a visiting professor to Indian Institute of Science, Education and Research, Berhampur. Before joining IISER, Berhampur, he was a visiting professor to Indian Institute of Science, Education and Research, Mohali. Sir had long association with Department of Zoology, University of Delhi, as a professor from the year 1978 to the year 2001, and before joining as Director of School of Environment Studies, University of Delhi. Sir has done his MS in the year 1967 from University of Hawaii, USA, and PhD from University of California, USA in the year 1972. His research interest includes ecology and behavior of zooplanktons and fish. He has been teaching undergraduates and postgraduates with his teaching interest includes ecology, aquaculture, ecotoxicology, animal behavior, and biostatistics. Sir has guided 10 PhDs and 12 MPhil students with more than 65 publications to his credit. Professor Rao was the editorial board member of several international journals like Aquaculture and Aquatic Ecology. Professor Rao has been awarded with several prestigious awards like INSA Teacher of the Year, INSA Teacher of Award for the year 2015, and he has also been awarded with Canadian Government Postdoctoral Fellowship and East-West Center US Federal Scholarship. With this brief introduction, I would like to invite you, sir, to deliver your lecture.
Okay. Fine. It is said that every has a villain and every conference engage. I'm sorry that we have been facing a lot of technical glitches, more from the speaker's side and then from the organizer side. Well, I think the introduction has been given. I'm sorry you're not able to see my face. Somewhere along the line, I'll show my face more fully.
We can see your face, sir.
You can see me too?
Yes, sir.
Oh, that's good. Okay, all right. Okay. Basically, already two speakers were there and we have given some extremely interesting examples of what statistics is all about. My namesake, but not with the same initials, Professor K.S. Rao has given an erudite lecture. So I don't think it's fair for anybody to listen to two Raos giving same erudite lectures. So this Rao will give an interesting lecture. Okay. This is my way of dealing with what biostatistics is all about. As I said, I'm about to say, I am not a statistician by any, and includes so many statistical luminaries, IIT professors and big shots like this. And I asked myself, what am I doing here in this? I'm an ecologist, rather a hardcore ecologist. But somewhere along the line, I picked up some interest in statistics because I thought that's one way of looking at day-to-day events in biology, in sociology, everywhere. So that's how I started. And of course, with a lot of teaching experience, I started appreciating the importance of statistics in not only in science research, but in day-to-day life also. So we'll start with a brief introduction. This is what the lecture is supposed to be. Statistics is everywhere, unbelievably in fields like this, of which we are all familiar, but in other fields also, such as quantum physics and physical chemistry. As if this is not enough, you see even in humanities and social sciences. Looking at all this big list, you start wondering, is there any area of human inquiry that has no relevance for statistics? I pause to see if somebody answers, but I will answer it myself. With a little bit of thinking, I feel that there is only one area that doesn't want statistics. In fact, if you mention statistics to this area, it will be almost blasphemy. What is that area? Religion, beliefs, faith, astha, or whatever you call it. That has nothing to do with statistics, and we don't have anything to do with that part of human inquiry, at least here. Okay? Why biostatistics? Is it any different from statistics? Well, as the term indicates, we simply say that statistics as applied to biological problems. Interestingly, humans are also biology because they are also organisms. It's one of the millions of species, Homo sapiens. So our behaviors, our way of acting in day-to-day lives, they all can come under biostatistics. This has been asked very often, and this quotation has already been given by Prof. And Mark Twain very liberally used Disraeli's quotation, but you can see now that we are talking about the third level of lies. That means the highest form of lies. And somebody cracked joke saying it's easy to lie with statistics. And I'm going to show in the next few slides. And it's also easier to lie without them. Of course, when it comes to statistics, none better example than our governments. They can produce all kinds of statistics for you. They in fact have a huge statistics department or even the ministry who crunches numbers, massive numbers, and comes up with graphs, trends, patterns, and sort of creates a kind of a magic about what is happening with their government, which you almost believe. That's why statistics can be made to prove anything, even the truth, they said. I want to give an example, a latest example, where we talk about COVID deaths. There has been a significant amount of underreporting. This is an example. You don't have to go through very critically what exactly this graph shows. But everywhere, throughout these almost 2 years, 3 years of the pandemic time, there have been cases where less number of mortalities have been recorded than probably actually that happened due to the COVID. Very nice statistical juggling can almost make you believe what they're saying is true. To give you a specific example, look at the statistics of cases. Look at the mortalities per million. Whereas USA, like 1200, 1300, Italy is 2000, ours is 162. How is it possible? A more dramatic illustration, see the graph. Pretty close. And now look at this. Number of deaths per million. Now, this statistics can help you appreciate this fact if you want to believe them. Should we believe them? Our government's motto is Satyameva Jayate. Truth alone triumphs. Does it? Do they always give us the right kind of quantitative information that we could believe? Can they say that their government is performing better than the previous government in terms of increase in food production, increase in literacy rates, etc.? So looking at that, you feel like just slightly modifying this motto. And I added this. In Sanskrit, kadach, that means kabhi kabhi it wins. Truth alone triumphs, perhaps once in a way. But to be fair, Indian government is not the only one. Most of the world over, lot of governments, lot of leaders have been presenting or underrepresenting the actual mortalities. In fact, US takes the lead. So this means now, starting with the highest form of our daily lives where we encounter problems with the government, you can see statistics could be used to do all kinds of mischiefs sometimes, but also give you true picture also. But scientists are not exempt from this accusation. This is a sad part of it. We scientists, which we belong to a profession which is supposed to be noble, scientists have been misusing statistics. This is part of the ethics in science. An investigative study done by Fennelly in 2009 revealed startling facts, unbelievable facts, disconcerting facts. 34% of the scientists surveyed admitted to questionable research practices. Questionable. That itself casts a shadow on our integrity. Modifying the results to improve outcomes? My goodness. Subjective data interpretation? You're supposed to be totally objective in science. Withholding analytical details, lest somebody find a hole in your analysis. Dropping observations because of gut feelings. You believe in something and your graph doesn't show that. Then you drop some observations, then the graph comes out all right. Some start with preconceived outcomes, notions how the trend should be even before they do the analysis. And that, of course, introduces subjectivity. We are daily confronted with the numbers everywhere. How do we make sense out of these numbers? Numbers become data only when their context is given. Let us look at some numbers. Just plain numbers. You can tell what they are. I ask you, for instance, what is 8 million here or 1.618? They are simply numbers. They don't make any sense. Now let us give them some context. That now makes sense. Wow, we have 1,349 species of birds. Whoa, that's a very sad statistic. 133,000 road accidents. This is unbelievable. I don't know how many are familiar with ocean sunfish. It grows to about 6 feet. And every year it produces 300 million eggs. Before you get scared, I assure you, out of these 300,000 eggs that even hatch, it's a great fortune for the mother if about 2,000 become adults. Heavy mortality. That's obvious, not surprising perhaps. That is sad. So much plastic dumped into the oceans, and we thought the oceans are just unaffected by human anthropogenic activities, but they have been discovering plastic everywhere in the deep oceans. That's another sad statistic. For people living in Delhi, that's a staggering number. The city where I live has a population of 408,000. That's 4 lakhs, sorry. as of January 2021, this is the total number of deaths, COVID deaths in India. And what is this 1.618? Can anybody guess? In an interactive class, in the classroom, I would look at them and just point out to a student and say, can you guess? Do you know it, or some such a thing? Now with 100 and odd or 200 participants here whose faces I will never be able to see perhaps, I just keep answering myself, So this is called the golden ratio. Look up in your Google search and you will find so much interesting aspects of Google ratio, this golden ratio. Anyway, torture numbers enough and they will confess to anything. That's a funny quotation. In other words, you get your data and just keep twisting in different ways, apply different methods of looking at them. Ultimately, you might get something that you were looking for. That's where you have to distinguish between real data and anecdotes. Many of us are familiar with or fond of telling anecdotes. You can believe them or leave them. But if you are telling something scientific facts, you have to support them with the data. This motto of the United States government says, "In God we trust." Wow, I don't know if we have to trust him or not. But somebody, a wise crack on this motto, he said, "In God we trust, all others must bring data." I don't think we should make exception for God also. Everybody has to bring data. If they want to make some statements, they have to be supported by data. Now I'll go through quickly a brief history of biostatistics as I see it. A statistician might have a different approach to proceeding, how he will look at the history of biostatistics. Well, and also it's a very brief one. Biostatistics, they say, took its origin sometime in 17th century in Europe. Where in Europe? Here. In gambling casinos. Then when these things started, people were asking, what is the probability that I can win a jackpot? Now people wanted to work out the probabilities, but the owners of these casinos don't want you to win all the time, otherwise they will simply go bankrupt. So you don't want to get too good at predicting or getting this idea when you are likely to win, what card will get you the success. So people were talking about how to work out these probabilities. That's when statistics comes into the picture. Earliest thinkers or casino players were asking these questions and probably posing these questions to mathematicians and say, can you tell me what's the probability of my winning this Las Vegas casino? The second one, where actually statistics might have started, is in actuarial statistics. Actuarial statistics refers to estimating the expected longevity of a person who is trying to insure his life. The insurance company has to know how long you are expected to live. If you are going to live for only the next 5 years, say 80-year-old or 85-year-old, and he wants to have a insurance amount for say 2 crores, his premium they would like to charge would be different than for a young person at 20 who wants to insure his life for the same amount. So every time a person goes to insurance companies and says, I want to take this insurance, they would like to know what is the probability of this guy living for another 10 years so that we can get all the money back through all these monthly payments. That's how it started. Okay, so now we go to Thomas Bates. This guy, very famous in his time. Unfortunately, he was not recognized. So-called Bayes theorem was not recognized until computers came into effect, because a lot of people felt it was very difficult to do all these calculations of the Bayesian probabilities, and so he was remained very obscure in the history of biostatistics until, say, about 50 years ago. Now everything is Bayesian. So in good statistics departments, you might have a course in Bayesian statistics. You have phylogenetics, genomics, proteomics, and whatnot. They're all using Bayesian statistics. Okay. Then we come to Francis Galton. I love telling stories about these people and in statistics in general. I don't know, that's my way of doing it. I don't do it in a totally scholarly way. I don't know. This Galton, of course, has dual credit. One of them, of course, is the cousin of Charles Darwin. But let us confine ourselves to his statistical contributions. He is probably credited with developing kind of a cause-effect relationship, or at least a correlation, a regression. How he developed is very interesting. Apparently, the story goes that as one travels from London to, say, Edinburgh or Glasgow, going through England and then going into Scotland, he noticed at every station where the train stops, he would look at the woman there trying to get into the train. He gave a quantitative index for this, the pulchritude, the physical beauty of this woman, and started noting down. Then what he found was, the farther you go away from London, the lower is the beauty index. This is a kind of a correlation or regression. But now, of course, if you presented this kind of statistics, somebody would challenge. But those days, that was very interesting. That means the metropolitan London girls were all sophisticated, fancy, makeup and all those things. So they tended to appeal immediately to the opposite sex. So that's how he apparently came up with this idea there are correlations. Then, of course, he went on to eugenics and fell into disfavor. And of course, Pearson is a giant in statistics, but a lot of tests have been attributed to him. We won't go into deep details, but I'm sure that subsequent speakers will be spending a lot of time discussing about his contributions. Of course, I must mention Fisher. He's a giant of giants. I would say that he is the Don Bradman of biostatistics, if you are a cricket enthusiast. He is not only a great statistician, he is also one of the founding fathers of what is called population genetics, which started out actually as an application of statistical techniques to biological problems, particularly genetics problems. So he has contributed enormously to the development of biostatistics. Particularly his contribution to analysis of variants are remarkable. They provided so many insights into the very problem of inheritance. We should not neglect Indian contributors because Indians are famous as statisticians. There is hardly any department of statistics in the United States which does not have one or two Indians or Indian origin. So I would mention Mahalanobis, the great statistician who was also an advisor to Prime Minister Nehru, and of course C.R. Rao, who recently celebrated his 100th year. How important is statistics for scientists? he said that it is the grammar of science. So you cannot construct a single sentence without grammar. You cannot convey your what you want to say if the English is poorly constructed without proper grammar. So it's the same thing with statistics. You cannot do proper science, you cannot communicate your results properly if it is not embellished or supported by statistics. And C.R. Rao is also very appreciative of what statistics is all about. All methods of acquiring knowledge are essentially statistics. Wow, that is unbelievable. Why do I need statistics in my area of research? I'm addressing this only to biologists, okay? There is a lot of variation in your population that you want to sample. There is variation in everything that you can think of, including the dilation times just our earlier speaker was talking about. Nothing is a fixed thing unless you're talking about identical twins or clones. Then they don't show any variation. But all of us mortals show variation, whether it is a plant or a E. coli or a whale or a sequoia tree, they all show variation because of the unique genetic makeup. Each has a unique genome. These variations are not only in your physical appearances, but they are everywhere in physiological and behavioral responses. You're talking about collecting some, people's response to some parameter or some TV show. There is variation in their how they feel about it. That's their behavior, that's their attitude, that's way of looking at things. As same in physiology, heartbeat is not the same for every individual. At any given time, we can say the average is 72, but believe me, there is enormous variation. Even in a sample of our class, say 40 students. So we can never sample, so we have to take a sample instead of the entire population. How do we account for this variability? Can we account and make a statement about the entire population based on a sample that we collect and gather the data? Okay. The second problem with our biology, they show uncertainty or stochasticity. Okay. And of course, we know what the stochasticity or uncertainty. Everything is certain. There is nothing certain in this world. Can you say, is there anything certain? I can think of only one. What is that? Every living organism, everything that is born or hatched or germinated has to die one day or other. Death is certain. Bhagavad Gita says, Jatasya hi dhruvo mrityuh. One who is born is destined to die. That's the only certain thing. But even with that, there is uncertainty associated. When you die, how you die, they are uncertain. Consider these. Birds have feathers. Malvaceae flowers are pentamerous. Those who are familiar with the pentamerous and Malvaceae, the familiar ones are hibiscus. These are pentamerous. Everything is in fives. Sodium atom has 11 electrons. Lord Mahavira was a vegetarian. Okay, all right. So these are all deterministic. There is no variation. Look at these. Mango starts flowering in January, normally, but not always. Migratory turtles in the state in which I am working now, beautiful display of enormous numbers of migratory turtles come in February, March, but not always predictably. Monsoon will be good in 2022. Can you be certain? Nobody can be certain. Even Modi government cannot assure you that monsoon is going to be good. Another probability thing, Modi will get a third term also. Is that probabilistic? Okay. So the conclusion is, in biological and social sciences, many process events and actions are probabilistic. Everything is based on probability. Now we can ask some random questions. You can think about this also, because you have to think in statistical terminology. You should have a statistical frame of mind if you want to be a good scientist. Every time you hear something, what you ask, what is the probability that this can happen? I ask some questions like this. What is the probability of this? Everybody is hoping it will peak and go down by mid-February so that we can return to normal lives. Will the beetle produce 250 eggs this time? We don't know. We ask only probabilities. What's the probability that a chain smoker will get lung cancer? What's the probability that your pet dog will live for 50 years? You ask questions like this. And you can also ask this rather delicate question. What is the probability RG will become Prime Minister in 2024? Everybody will simply say probably, well, probably, yeah, maybe, but nobody can tell you that this will happen. So these are the two things that makes you require statistics for taking care of these two major headaches in biology. Third one is, how do we get data that will tell us something, some parameter about the population? Can you ever sample the entire population? Obviously not. There are some, even mosquitoes. You want to make a statement about mosquitoes, for instance. How long do they live? What is the size of the female? Do you mean to say that you have to measure the size of the females of all the individuals of the population? Even my bedroom seems to have large sample of mosquitoes which bother me at night. It could be 1,000 trying to suck my blood. And imagine the whole city of Berhampur, it could run into billions of mosquitoes. So what you can do is take a random sample and see if you can make some conclusions which are meaningful, which could represent truth. So you have problems in extrapolating from sample to population. That is one of the problems faced by statisticians. How to extrapolate from sample to population, from sample mean to the population mean, mu. How do we make sure that what the statement you are making based on a sample is true for the entire population? With what confidence can you make that statement? There is a Sanskrit nyaya called Sthalipulak nyaya. I use this not to show off my Sanskrit knowledge, but to illustrate the idea that there are cases where, to see if the entire population statement about it, just you need to take only one individual. Sthali means cooked rice. Pulaka is one grain. So to see if the whole rice is properly cooked, the housewife does not simply pick up everyone, and press it and see if it is properly cooked. She just takes one or two grains, presses and says, yes, it's well cooked, ready to eat. So can we take two individuals at random in a college, ask them what they feel about Shah Rukh Khan or Kareena Kapoor, and make a statement about the entire population of the college? Doubtful. So basically, you ask yourself what kind of statistician you want to be. It's not my analogy, but somebody has used a very nice analogy, like building a home or house for yourself. There are different levels of doing this. One is an architect who makes his nice blueprint for you, tells you what kind of things you want, and he makes it, and he designs it for you. Worker goes by that. That means the engineer helps you to bring the bricklayers, the mason, the carpenter, and all those things. Third level, do it yourself. Small things, you can do it yourself. I just leave it. I can take care of that, and you help with the help of your wife or children. You start putting those things together, etc. So let us see what they mean in terms of our biostatistics for data analysis. This architect equality is a statistician who contributes to the theory of statistics. These are the famous people that generally are found in statistics departments. They're always working on some new formulae, new theories, new equations, etc., to see how best we can analyze data in different situations. Most of us do not want to be that because we leave it to statisticians. Many of us are not good at that because we don't know enough maths. Somehow we get lost when we see equations, but we want to be a skilled worker and make use of them. So you have a situation, you have a set of data, you have a hypothesis you want to test, you would like to know what statistical test has to be used, and then lo and behold, this guy statistician already has worked out something that might be right for you, and you take that, apply it, and solve your problem. And this is another one which a lot of present generation people are doing without understanding the basics of statistics. Are those guys who simply press a key and get their standard deviations, F tests and conclusions and cluster analysis and what have you, because they have a fantastic statistical software built into it. This is what I don't want our youngsters to be. Without understanding what you're doing, do not start pressing the keys and generate fantastic graphs in whether it's R software or Excel or something like this. That's like building a fancy edifice, a koti, without adequate foundation. Somewhere along it's going to crumble. Another problem with biologists is they go to the statistician for help after you collected all the data. You finish the experiments and you say, okay, I'm ready to submit my PhD thesis, and you go, I want to analyze this data, but I don't know how to go about it. You go to a statistician. That's what irritating to the statistician. You're supposed to go before you plan your experiments, so he can tell you what is the optimum way of doing it, what is the optimum sample size you would need to reach the conclusions that you're expecting. That's not happening in most cases. We go to the statistician and say, can you help me analyze this data, please? Okay, I'll try to wind up. And so other problem with most of them use statistics the way a drunken man uses a lamppost. Okay, more for support than for illumination. That means they collect data, they have some conclusions or pre-expectations, presupposed notions, and they look for statistics that will support their observations or their conclusions. In fact, it should be the other way. Statistics illuminates, gives you more insights into your biological problems. That is not being done, unfortunately. Any novice authors believe that their research reports become more publishable if it is fortified with embellished statistical results. Recently, it has been pointed out, if you look at some papers that are accepted in prestigious journals, lots of, in brackets, p-value less than 0.5. The more they see these things, it looks more publishable and looks more authentic, more standard kind of thing. But that's a misnomer. It's like sprinkling a little Ganga Jal just to sanctify the whole house. Okay. Another problem is what I call statistical overkill. When a simple statistical test will do, you go for some really fancy, sophisticated, complex statistical analysis. Why? It's like if you have a nut to crack, a simple hammer would or a stone would do, and you go for a sledgehammer? This is the tendency because they don't have to do this manually. They'll simply go to a statistical software and they can do very, very fancy analysis even if they don't understand the basics of it. Okay, this I will skip then because if there is time is a problem. I'm just talking about here the inductive and deductive methods of doing science. This is a very well-known Popper's approach to science. He talks about falsifiability and verifiability. It's very unfortunate. Constraints of time are forcing me to go through these things. Interesting slides. Too bad. Okay, this is important. A hypothesis is an explanation. It must be testable and it must be falsifiable. That's testable. That's not testable. There's no way you can conduct an experiment or just see if that's a rationally subject opinion or a fact. That's testable. That's not. You just read it and ponder over it. In case you haven't encountered this word pulchritude, it refers to the physical charm of a person. As I said, they must be quantifiable. If you can't quantify an observation, you can't do any statistics on them. Yeah, these are quantifiable, so you can do some analysis on them. Some are not easily quantifiable, but you could find some way of quantifying them, but these are not easily quantifiable. Like, this guy says, I love you, and she says, how much? Can you quantify this? One of my students said, sir, one way to do it is to say, so much, and put a lot of O's, so much. I don't know, that is applicable. Here is another example. Honey, your singing is terrible. Huh? How terrible? Could you quantify this? Okay. Sometimes setting up a hypothesis. You can set up a simple hypothesis why this lady gets up with a splitting headache. Maybe she had an argument with her husband or boss at office. Maybe she has some mental tensions with some other problem, or maybe she has a brain tumor. So, science tells us choose the most plausible and the simplest possible hypothesis. That's called Occam's razor or the parsimony principle. Unfortunately, this I had to skip. Could the organizers allow me a little more time, 10 more minutes than the deadline you are giving me? Just 10 more.
Sure, sir.
Oh, kind of you. Okay. See here the way you set up a hypothesis and plausible hypothesis and see how you can test them. These two girls, I named them what? Rani and Vani. In some other lecture, I used the same girls. I called them Sita and Geeta for a change because everywhere there is variation. They both attend the biology class at every day at 1:30 to 2:30. Just keep reading so I don't have to waste time reading them. So three things are happening. They're sitting in the back row and they both feel sleepy during the class. Why do they feel sleepy? You have to set up a hypothesis and test it. One is They both have heavy lunch before class, and so they makes them feel sleepy. This probably the class happens because when I take a class at 2 o'clock, generally these students are more drowsy and sleepy than if I take a class at 10 o'clock in the morning. So that probably is true. They both sit in the back seat with less scope for interaction with the teacher. So when you are in the back of this, all the way in a big classroom, chances are the teacher won't probably ask you any questions. Excuse me, raise your hand, I want to ask you something. No, generally he tends to see those in the front. So that is one way. You can then drowse off. Third one, the classroom is too warm and no ventilation. Sometimes that also makes you warm, feel sleepy. There is another possible hypothesis which most of us teachers are not willing to consider. That is, the teacher is simply boring, that makes you sleepy. How do you test that? Anyway, so you can just switch them because they're twins. So you make one eat lunch before, the other after the biology class. Then what should happen? Vani should get sleepy, not Rani. Predicted result. Rani should get sleepy during chemistry class, which starts at 2:30 because she had lunch at 1 and then went to the chemistry class. Like this, you can test. Back row, you just can move one of them to the front and one you keep in the back, and again you test who feels sleepy and who doesn't. So, okay, I'm going to finish soon. This probably somebody is going to deal with the type of data that you collect, because you have 5 weeks of lectures by more eminent people, more informed people, more erudite statisticians. They will discuss at length all these aspects of what kinds of data are collected categorically in attributes. So this is important thing to realize. When you are sampling, you should try to see about bias and variability. Here the bias is large. The truth is the bullseye, okay? Here, not only the bias large, the variability is also high. They are not all together. Here, variability is high. They are all spread out, the observations, but bias is small because it's so close to the truth. Most ideal would be this. Bias should be small, variability should also be small. So you try to ensure that these two things are taken care of when you're collecting data. Finally, okay, organizers, I am keeping my time. I'm using the last slide almost anyway. Okay. Students ask, in fact, I was one who asked my own advisor, sir, I want to take statistics. It seems to be a very interesting subject, but I don't have maths background too much because I come from India. He asked me some simple arithmetic questions and asked me to do it there, right in his presence. I did them because they were simple, high school level questions. He said, Rao, you don't need anything more than this. For biostatistics, you don't need any big, because we are not interested in developing equations. We are not expecting to derive them, provide proofs or anything. We want to take the statistical technique that they made available and see how best we can apply to solve our biological problems. Right? So, if you see a blackboard like this, you can be sure this cannot be T.R. Rao's class. I do not put any equations, nor do I feel apologetic that I am not doing that. Sometimes my student point out, sir, what kind of statistics is this? I said, look, this is what I teach, because how to apply statistics for solving biological problems. If you want equations and all those things, I can provide you. I can provide them and you can make use of them. You can get confused. You can become enlightened. But they will not, you will not be any better biostatistician. Okay. So thank you very much. I did a rush job, but at least you let me finish my talk. Thank you so much.
Thank you, Professor Rao, for such an interesting, intriguing and lecture with self-explanatory slides. Thank you very much, sir. Now I would like to invite Dr. Zishan Ur Rahman to instruct our participants about the workshop. Over to you, Dr. Zishan, and thank you very much, sir, again.
My pleasure.
Thank you, Dr. Ruchi. Am I audible?
Yes.
Thank you, sir. I extend my gratitude to the distinguished speakers for sparing their valuable time with us. Also, thanks to all the participants for their interest in our workshop. The instructions for the registered participants are as follows. All the future communications will take place only through the Telegram group. Therefore, I request all the participants to please join the group if you still have not joined. The workshop includes 3 live sessions. The first session is the inaugural session, that is today on 17th January. The second live session will be an intermediate session that will take place on 30th January on Sunday. The last and third live session will be a valedictory session, which will be the last day of the event. For a convenience, the workshop can be divided into 5 weeks. Each week includes some recorded lectures and an assessment based on the lectures of the 5 days of the week. The 5 days of the week from Monday to Friday will be for the lectures and Saturday will be for the assessment. All video lectures are recorded by our distinguished speakers, especially for the workshop. They will be available on our official YouTube channel, Phyto Zakaria. The link of the recorded video will be shared on the Telegram group. You can ask your doubts and questions from the recorded YouTube video in the comment box. The link for the assessment will be shared sometime around afternoon on Saturday. This form will be available till 11:59 p.m. on Sunday of that week. Also, there will be a feedback form along with the assessment sheet every week that is also mandatory to fill. The assessment will be based on multiple choice of questions. Each assessment will carry 25 marks. There will be no negative marking for the evaluation. It is mandatory to submit the assessment of all week for your valid certification. If you miss any of the assessment, you get disqualified for certification. There will be an additional assessment, the final assessment, other than weekly assessment. The final assessment is based on the lectures of all 5 weeks. They will be based on the MC. They will also be based on MCQ. The final assessment will carry 75 marks. The link for the final assessment will be shared after the valedictory session. Also, there will be a final feedback form along with the final assessment sheet. The successful completion of the workshop will bring a graded certificate for the registered participants. The graded certificate will include grades like A+, A, B+, C, and so on, based on your overall performances in the assessment of all 5 weeks. The employed registered participant do not require any NOC to participate in the event. If you have any doubt and query, please write us on email ID as follows. The ID is z.rah@manh@du.ac.in. We look forward to your active participation. Thank you. Now I request the convener of the workshop, Dr. Savindra Kumar, to give a vote of thanks. Over to you, Dr. Kumar.
Thank you, Dr. Jishan. Am I audible?
Yes, Dr. Kumar.
Okay, thank you. So before I say formal vote of thanks, I must say sorry to Professor Rao because of the time crunch. But yes, I would like to say one more thing to all the participants that don't worry, we will have more live session with Rao sir, so we can clear our all doubt at that time. So thank you once again, Dr. Jishan, and good evening, everyone. Thank you is such a prayer that cannot be seen or touched. It must be felt by heart. I, Dr. Savindra Kumar, from Department of Botany, Jacques and Delhi College, feel honored and privileged to get this opportunity to propose vote of thanks on this special occasion. I would like to thank our Honorable Chief Guest, Professor K.S. Rao, Guest of Honor, Professor T.R. Rao, and our keynote speaker, Dr. R. Sundaram, who blessed us with their presence and gave their valuable time from their busy schedule to grace this inaugural session of the workshop. We also wish to express our gratitude to our distinguished speaker, Professor Suman Lakhalpal, Head Department of Botany, Professor V. Srinivas, AIMS Delhi, Professor Gyan Prakash Singh, Banaras Hindu University, and Dr. K. Venkatraman Bhatt, ICAR, NBPGR, who will enlighten us in coming weeks. Words are not enough to thank all our resource persons for adorning this workshop by sending the recorded video lectures well in time. I must just say a special thank to all our resource persons, because when we were planning to this workshop, that was the first thing in our mind, that whether we will get the video lecture in time or not. But yes, I would like to say thanks one more time to all our resource persons for sending timely videos. Without their constant support and inspirational thought, it would not have been possible to conduct this workshop. Organization of an event is impossible without the support of the head of the department, head of the institute. I, on behalf of the organizing committee, convey deep regard and heartfelt gratitude to our honorable principal, Dr. Sangeeta Pandita. I am very much thankful to all our faculty colleagues and non-teaching staff members who always stand by us and motivate us. An event of this dimension cannot happen overnight. The wheels start rolling months in advance. We have been fortunate enough to be backed up by a team of very motivated and dedicated members. I cannot thank everyone enough for the involvement they have shown and willingness they have expressed to take on the completion of tasks beyond their comfort zone. Finally, I thank the wonderful participants who have turned up in such a great numbers across the country for showing their interest in this workshop. We have received a pan-India response across the universities and institute from Kashmir to Kanyakumari, Gujarat to Guwahati, and experienced scientists to first-year undergraduate students from different fields like biotechnology, management, pharmacology, BTech, population science, and obviously from botany, zoology, and life science courses. Thank you so much for your interest and participation. On behalf of the organizing committee, I would like to ensure that in coming 5 weeks, we will try our level best to make every session a rewarding experience. With these words, I firmly end today's session. Have a great evening and goodbye. Stay safe. But before you close your window, let us take some group photographs. I request Dr. Ruchi, can you please allow the camera to have all the participants?
Yes, I have already allowed. Everyone can switch on their camera and mic as well.
Thank you, Dr. Ruchi.
Participants can also take the photos.
That's nice. I wish you could show the names also below.
Yes, sir. The names are also coming in screenshots.
Ah.
Thank you, everyone. Thank you for your patience. Thank you very much. Now you can leave the meeting. Thank you very much. Thank you, all of you.
Thank you.
Bye.
Bye-bye, everyone.
Thank you, teachers.
Bye.
Thank you, Professor.
Okay, bye.
Thank you so
Sir. Thank you, organizing committee. Savindra sir, thank you. Thank you, Savindra sir.
Thank you.